Yesterday we saw this. The old.
And I will give certificate today to those only who appeared in both exams.
Okay, the old tricks. New tricks to old dogs. We saw this. And review, we've seen LTV models. Already you should be experts in these models. And okay, so we did something classification. Did this yesterday. In fact, this is a review of what we've already seen. Now the issue of observations. It's also very interesting. Yesterday I showed you how, well, this we have not seen in detail, but the point is that you get the idea. The idea is that you have to find a relationship between, you have data. It shows you the redshift of a supernova, and then you have a model to calculate what would be the luminosity distance for that supernova. But and that has to match the luminosity that distance that you obtain from observation. And so this is, if we have FLRW geometry, this is only possible if we put a cosmological constant. But with LTV models, it's also possible because the geometry is so different, it's sufficiently different to allow fitting this data, right? Now, before continuation, I would like to, two things. First, I saw yesterday your papers, and I'm going to very, very quickly discuss the questions, very quickly, just to give you the answers for this, so that you more or less have the feeling whether you wrote correct answers or not. And of course, some of you wrote complete encyclopedias. So, and complete encyclopedias in handwriting are difficult to read. It's like Egyptology. So it will take me some. I would like to return your papers with markings, so that you know what you did. So some people made some crass errors there, so I would like them to know that what they wrote is wrong. And I'm going to say this very quickly. And somebody sent me an email yesterday with questions. One of these questions is important, so I will also discuss it very quickly. Okay, explain how we characterize time and space in a cosmological model. Is this characterization unique for each model? This was a very simple question. Still, and people wrote an encyclopedia on coordinates and the space-time and Minkowski and Einstein came from the roof and made a big lecture and so on. No, this was very simple. The form velocity, which is tangent to the whirl lines of the observers, these are the ones that define the time axis. And time is their proper time. And space is the surfaces orthogonal to them. See? This is how we define space and time in a cosmological model. That's it. That's it. All what you had to say was that. There was no need to write such an encyclopedia.
So each question carries 15 marks.
Each
question carries 15 marks.
Yeah, but very few answered it correctly. You know, there's a big encyclopedia. And then you miss the right answer. Come on. Now, the issue is this, and I ask you now this question. This is possible because cosmological models have matter, right? Cosmological model is, here we are navigating in a galaxy, right? Navigating. That's another galaxy, it's also navigating. That's another galaxy, it's also navigating. So you take all these whirl lines, they move around, and we have clocks in our ship, so that's our proper time. And if you collect all these whirl lines, you have a time axis everywhere. At every point in space, there is a time axis. And that's your time coordinate. That's a co-moving frame, right? And then the hypersurface is orthogonal to that. That's what you call space. And it is not unique because you can always assume that there is another for velocity. For example, for another matter component. We can talk about the co-moving frame, the frame that is co-moving with the galaxies, with cold dark matter, or the frame that is co-moving with the photons, right? So it's not unique. It's not, and we can also change it arbitrarily and define another for velocity. And then we would have another time and another space.
So it's only representation is different now, but basic space and time is the same now. Basic idea of space and time is the same, but only the representation is different.
Only what?
Representation.
The representation.
Of the space time is different for different model, but the basic idea of space and time will be the same.
You have one cosmological model, Kantowski-Sachs. That's it. You define the for velocity is what defines the whole thing. The for velocity defines the time, and surfaces orthogonal to it define the space. Now, one question. Think it carefully. What would happen in a vacuum space? Can we do the same? In a vacuum space, Schwarzschild. There is for velocity, right? Or we can define it for velocity. Yeah, we can, because we can put test particles there. And the test particles have for velocity, right? See? And with a family of test particles, we can define time and space. Typical test particles in Schwarzschild, static observers. They were observers or observers in circular orbits, right? Or observers without orbits. They simply stay put, stay static where they are, right? So these observers, they also have a for velocity, but it's not going to be geodesic because for them to be static, they need not to fall, right? They cannot fall. They have to be static. They need a for acceleration so that they don't fall, right? But these observers also have whirl lines. And this whirl line defines the time. And the surface orthogonal to that defines the space. But you can, for example, throw objects radially to the Schwarzschild black hole. And then these whirl lines would be geodesics, radial geodesics. And they also define, if there are whirl lines, they define the time. And surface orthogonal to them define a space, which would be different from the other one. So what happens in a vacuum space? In a vacuum space, this co-moving frame only works for test observers because it's vacuum, there's nothing, right? So it is arbitrary. In a cosmological model, it's not arbitrary. There is a preferred frame, the frame of the cosmic observers, see? Let's say the frame of cold dark matter. We can say that's preferential, right? There is a physical argument because cold dark matter, galaxies, clusters of galaxies are moving there, right? There's another frame, the CMB. But all these frames are defined by matter energy, right? So they're not arbitrary. We cannot just assign any for velocity. That for velocity has to represent actual matter, or matter energy moving there, right? In a vacuum space, they're all test observers, so it's none of them is preferential.
But sir, introducing test observers will again introduce matter.
No, definition of test observer is an observer that does not change the geometry.
Okay.
Yeah. Otherwise, it would not be test observer.
Yeah.
It would be Yeah, that's a very big difference. Here you have Schwarzschild black hole, and then you put a, of course, test observer it doesn't exist. If the sun is there, and I send this little thing over to the sun like this, strictly speaking, it will modify the field, right? But the mass of this is 1 gram, and the mass of the sun is 10 to the 33 grams. So the sun doesn't care, doesn't even know that I'm throwing this to, here, throw this to the sun. The sun doesn't know about that, right? So that's a test observer. Strictly speaking, that doesn't exist, because even one atom would change a field. But it would change a field to such a small degree that it's negligible. In fact, it doesn't have to be 1 gram, even one asteroid. Even the Earth can be seen as a test particle for the sun. But it's also a very good approximation, right? So, test observer is a concept. It doesn't exist in nature, but a lot of systems approach test observers. There are good approximations, right? So, in a vacuum space-time, a comoving frame can always be constructed with a family of test observers. But because the test observers are arbitrary, I can put any type, I can take Schwarzschild and put any type of test observers I want. There is no limit to that, right? Some of them will have nice geometric properties, but they are test observers. In a cosmological model, you cannot put matter arbitrarily. Cosmological model, the matter is already there. We cannot force all dark matter to collapse if it's not collapsing by the geometry of the model. I don't know if you understand. Once you have a cosmological model, the matter itself is giving you the form velocity, right? Once you have a cosmological model, the existence, the presence of matter energy is defining a form velocity for you, right? If you have a vacuum space-time, you can put any form velocity you want, right? Okay, so that's important. Another point. Okay, explain and describe Kantowski-Sachs models. Write everything you know about them. Here, that was my error. Write everything you know about them. Produce pages and pages and pages and pages and so on. I should not have said that. Sorry, I didn't know that. Different style. The Mexican student, you have to force him to write things. They write very little things, 3 lines. Say, please explain more. Please explain more. Here, it's the opposite. Don't explain so much. That was an error. Sorry, you didn't know. No, that was more or less well answered. Most of you understood. This was the best answered question, right? Now, you understood. It's some people made some errors, like somebody said the symmetry group was SO4. I don't remember who, but no, it's not SO4. It is SO3 times R. See? It's a 4-dimensional symmetry group, isometry group, formed by the group that generates spherical symmetry plus another translation, you could say. Why it is not SO4? Because it is not a 4-dimensional rotation, right? 3-dimensional rotations plus translation is not 4-dimensional rotation. It is also not SO3 cross S1, because the extra killing vector is not cyclic. See? That's the difference. For example, if you have, that's another thing I want to comment. If you have axial symmetry means there is an axis, and if you circle that axis by a circle, S1, not 2 spheres, but a circle, then the field is identical, right? So the symmetry group there is 1-dimensional, but the orbits are closed. If the orbits are not closed, then it's not axial symmetry. So it is important the dimension of the group is not all what matters. We also need to know what is the geometry of the orbits, right? Okay, so that was correct. That was correct. Then, explain the difference between Kantowski-Sachs and LTV model. That was also more or less okay, but some people got things, some people even wrote Kantowski-Sachs metric depending on radius, which was wrong. But that was more or less correct, the well answered. I think you understood that one model, Kantowski-Sachs, are anisotropic but are homogeneous because once we, because it has three ignorable coordinates. So the only non-ignorable coordinate is the is time. Therefore, Kantowski-Sachs is homogeneous because as long as your symmetry group does not include time and it is three-dimensional, that's a correct definition for homogeneity, right? Now that doesn't mean, well, again, this means that there exists a coordinate system in which the metric only depends on time. That means it's homogeneous. But LTV models are not homogeneous because the orbits of the symmetry group are two-dimensional. This means that time and one spatial coordinate are not ignorable, and therefore it's not homogeneous. That was answered correct. Kinematic meaning of expansion, shear, and for acceleration. That was also, I think it was understood, the basics was understood. But that was also meant to be a very short question. Yeah. So the thing is that, no, and I'm telling you this is a very serious advice. Don't do that. That gives a very bad impression. It's like, for example, I'm lost in Delhi, and I'm looking for a direction. So I ask Sushan, or I ask anybody, how do I get to street X and Y and so on? And let's say the instructions are not complicated. The instruction would be walk 3 blocks to your left, and then 1 block to the right, and where that exactly the place when there is a gas station, that's opposite the gas station. Okay? So I ask the person, and the person tells me all the story of Delhi and how the whole neighborhood began, and that 3,000 years ago there was some catastrophic event, and then he tells me all the traffic regulations of Delhi, and then keeps me there for 1 hour. It doesn't tell me what I want to know. This is horrible. Don't do that. It's very bad that and it's also sometimes it's perceived as a disguise of ignorance. Like if I don't know the address, it's better to say I don't know. Ask somebody else. I'm not sure. Rather than to give a very long story. Don't do that. Be succinct. Learn to be succinct. See, in case you are asked to say, write all what you know, then write all what you know about the models. Right? Not about general relativity and about arithmetic and about the story of India and the Brahmins and so on. No, be succinct. Learn to be succinct. That's a very good, I think you should follow this advice. Don't do that. It causes a very bad impression. Right? If you do it in your careers, learn to be succinct. To answer.
What is the succinct?
Concise.
Concise.
Concise, okay.
Yes, concise. Go to the point.
Point,
Go to
yeah,
the point.
okay.
Don't people ask you one question. Give first a simple answer. If that's not enough, elaborate. But don't do the opposite. See, don't do the opposite. If they ask you simple question, don't give the complicated answer. Give first a simple question. And in fact, you can say, somebody is asking you, professional exam, whatever. What is something like, what is a Kantowski-Sachs model? Say, Kantowski-Sachs models are characterized by this image. You can say to the person, I'm going to give you first a quick answer, and if that is not sufficient, I can elaborate further. Give the quick question, the quick answer. Should say very concise, to the point. And then what you will see is that most examiners will say, okay, enough, enough, enough. If they see you are secure of yourself on the quick answer, most people will say, okay, okay, no more, no more. Why? Because you will see as you get more mature, you will see that being an examiner is very boring.
Yeah, yeah, that's right. Yeah.
So once you see the student with confidence and that is dealing with the points, right, to the points, to the concise points, say enough, because you don't want to be there listening to a lecture of 2 hours about Kantowski-Sachs models, right? Okay, so do that. That's a good advice. Don't do this strategy. Very bad. Write encyclopedias. Don't write encyclopedias in your exams. Go to the point, right? Okay. Another thing. Write everything you know about. Again, write everything about. Okay. Sources with non-zero pressure. Perfect fluids. Yeah. Some people, in fact, I noticed that you sort of memorize the notes, like it's already repeat there. Anyway, so one question, I think you asked me this question, very, very interesting question. How come you can have anisotropic pressure in a spherically symmetric fluid, right? Because anisotropy is like something that is bent, that is crooked, that is, you can, like spherical symmetry is very simple motion. There is only radial motion. So where is the anisotropy? Well, the anisotropy is radial. See? It's like, imagine that you have matter, and in spherical symmetry, this is the center. This is the center. So, center is 1 point. Here is the center. So what can matter do? Like this, it's radial. See? If matter would do like this, then spherical symmetry is broken. Matter cannot move like this, because then it cannot be any longer spherically symmetric. To be spherically symmetric, all motion has to be purely radial, right? Okay. So where is how can we have anisotropy of anything? Like say, how can there be shear? Shear is deformation. Shear involves anisotropy. It's anisotropy of the expansion. Shear is essentially an anisotropy of the expansion. So how can there be an expansion that is anisotropic when you only have radial motion? Well, imagine that there is a very small cube that is moving away from the center, right? Now, the cube will only move radially, but the cube can become an elongated cube as it moves radially, right? Or it can become, see, do you see how where the anisotropy is? It's in the radial direction. See, the deformation of the volume would be in the radial direction, right? See, initially it was a cube, but as it moves, the cube becomes more elongated in the radial direction. And this is how you can have anisotropy in spherical symmetry. It's not, the anisotropy would not mean that the cube deforms like this, because that would violate spherical symmetry. All the particles in the cube are moving radially, but in such a way that volumes defined by these particles become elongated in the radial direction. This is something important, because some people say, well, they think that all spherical symmetry has to be without shear, without deformation, because they think deformation will necessarily violate spherical symmetry. No, what happens is that spherical symmetry imposes a very, very special type of deformation, which has to be radial, okay? So that's, I think that would clarify
But
that.
the shape of the sphere will not deform, no?
Yeah, that's right, exactly. You see, all these little cubes define a sphere, right?
Yeah.
All of them.
Yeah.
Now, the next one, the cubes will be radially elongated, but the collection of them will still define a sphere.
Yeah.
That's right. Okay, so let's.
Yeah, just I would like to just mention some of the things which you have told about the question paper, no? That it is always better to be concise and
Yes.
okay. But just I think on behalf of everybody, I would like to mention, because I have shared their views during
Yes.
the exam time and all.
Yes.
So what happened that of course I mean, we are doing here and you are teaching is very good and everything, but the thing is that there was so much of matter in this
Yes, yes.
PowerPoint, and all the time we were busy here.
Yes.
Means from morning to around 4:30,
Yes.
and of course for some of them this is totally new.
Yes.
So means what they feel, and we also, I myself also, that means rather than exam, if we could have something like a group discussion or
Yes.
something presentation,
Yes.
then it would be good. But now it's okay, we have done all these things, but and all the people were really very anxious that what to do with all, because you cannot remember all these things.
Yes.
So people have tried their best rather
Yes.
than to say no to this exam.
Yes.
So they and all the people were, some of them are very tense also, and in fact I have heard the one boy was telling that I have memorized all these 19 slides. Means pura I have marked up it. And so it's okay because they are helpless of what to do. But
Yes.
anyway they have to appear.
That's
So
true.
they what I want to say that they have tried their level best.
Yeah, well, I see there's pages and pages and pages.
Yeah, but
No, they are well written. I'm not saying it's rubbish.
No, but what I want to say that rather than not writing anything, they felt that what are the things which we are knowing, we will write it,
Yes. Yes.
because they cannot put the total empty sheet, no.
Yeah, no, I understand. There was a communication problem, because now I realize that I should have given less material and more exercises.
Yes.
And sir,
Exercises
a
section.
small suggestion, sir. Actually, if we had an assignment after every lecture, we
Yeah.
would have really
Yes.
supplementary
Yes.
because we would have an algorithmic form of knowledge in our head. Otherwise,
Yes.
it was like gold on donkey's back.
No, that's true. That's true.
And
It's,
another thing I would like, because these are not all the formal courses that these are in some books or that. So if we get the material in advance,
yes.
means before this lecture started, then the people who is really interested in learning, they will just go through little bit, they cannot understand. So doing means while you are teaching, they can understand around 70%.
Yeah, that's true, because the confusion is that, and that's also from my point of view, it was long enough to be a course, but not long, it's long enough, the question is the difference between a lecture, sort of seminar, and a course. This was too long to be a seminar. And my error was that I prepared it as a seminar, right, without exercises and so on. Because my idea was that it was going to be something like a very short course. But in the end, it's...
No, it's okay. Means everybody have tried our level
No,
best.
but-
So this thing can happen. So means what
Yes.
on behalf of them, I would like to mention, because I have shared their views with them.
Now, what I can do for the future, if you are interested,
Yeah.
is that I can send you exercises.
Yeah, sure, yeah.
Please, sir. that would be-
I
On
can-
these things.
Eh?
On
On these things, yes,
whatever
yes,
we have
yes. I can send you exercises. First thing I would like to do, also with calm, now in the future days that I will be more relaxed, to send you an email with the answers to this question.
Yeah, that would be also very nice. Yeah.
And then to give you like a collection of exercises to do, yes, calculations, exercises, and so on. That these exercises can be taken from books, because also I have not given you a bibliography, which books are
Yeah.
Mm.
Essentially, the best book for the material I've seen is a book by Martens, Ellis, and McCallum. It's called Relativistic Cosmology.
Yes.
It is published by Springer Verlag. That's the best book That's the best book, because other books now are too concerned with observational cosmology or with inflation and so on. Not with this type of cosmology. It's the only book in the market now, and it's a very good book. I strongly recommend it.
Ellis and McCallum.
Ellis, McCallum, and Martens. I don't know the order of the authors. I think it's Ellis, McCallum, and Martens because alphabetical. But, so that book I recommend, and that book itself has exercises.
And sir, just I would like to, just you also think over, but what I feel that, in fact I mentioned in my speak also, that rather than this type of formal exam, we can have some more innovative ways. If suppose if I like LTB models very much, then I will study it in a nice manner and I can just give some maybe 10 minutes, 15 minutes that what are the best feature of this.
Yes.
So I will go deep in that and I will share my experience with these people, and
Yes.
whatever I am means making some mistake, you can correct me.
Yes.
So
No,
what-
I understand. That's like oral presentation.
Yeah.
Small oral presentation.
Small, yeah.
Rather than the written exam.
Yeah.
But the problem is that we're like 40 or something. You're like 40 people. So if each one takes 10 minutes, that would require like 3-4 days. See,
No, but
that's
we
a
can
problem.
maybe we can do in some groups or maybe something.
We can
Yes.
do it ourselves. Maybe.
Yeah.
We can do group
Yes,
activities
teams.
ourselves.
Yeah,
Teams.
maybe
Team.
teams, then we can arrange some group discussion.
Yeah, that's true. But look, now that's all hypothetical because
No, but no, this is the lesson for our future thing.
for future, yes. But to be practical, what we can do now, in this case, see, I still have some material I want to show you that is important. So, and I'm a bit on a hurry to show it. Now, what we can do for the future is I can send you, I think it's better because, you know, to be honest, all the material that you wrote is too much to read. It's
Yeah.
very complicated. So it's better that I supply to you a detailed answer of the
That
question.
would be best. Yeah.
A detailed answer, even if it's handwritten. I
Yeah.
have nice handwriting.
Yeah, yeah. No, it would be very good rather than computers.
Yeah, you don't need Egyptology or anything to understand my handwriting. I do it by hand. I give you a very nice reply of a response to all the questions, and then you yourself can grade yourself. We are going to assign grades. Nobody failed. We are going to assign grades, right? I divided the whole in 2 groups. Like group A is a little bit better answered, and group B is not so good answered. But all of them will pass. No one complains. The student goes to the union and says, "Oh, violation of human rights. I'm the teacher." Don't want that. So, but see, the marks, the judge should be yourself, right? See? Sometimes students come, and I teach in low semesters, first and second semester. Student comes, tear in the eye. I'm going to lose my grant. Please, please, please. I say, okay, you want a number, here's the number. But for your own sake, you should correct this problem. Especially if the student is terminal in the sense that he needs to pass this exam in order to do something else that is not related to physics and maths, like engineering students or architects or whatever, that they have to take calculus. Calculus is a monster for them. So, and they have no time. It's like this question of talent. You should know it's true. Some people have it, some people don't. Sometimes it's hard for people to understand that some people have talent for mathematics and physics and some people don't. But it's normal. Like if you are organizing an orchestra, you know that you pick up somebody randomly in the street and they have no ear. Say, okay, sing happy birthday to you. And they will say, happy birthday to you. So they have no ear. no ear. Some people just don't have talent for music. Or you are organizing a dance group. Some people can't dance. There are problems. Or you are organizing a football, soccer. Some people don't have the talent. They are just too clumsy or whatever. You are organizing runners. Some people cannot run. Somebody who is 100 kilos cannot run. It breaks his knees, etc., etc. And the same thing here. So again, sometimes people have no talent. They need the grade. I give them the grade. Now, the grade, the important judge is yourself. If you get a grade, don't think that maybe the grade is more than what you really know, and it's up to you to correct it, okay? Because if you don't correct it, later you'll have to pay, right? Say if you get a grade that you do not deserve, okay, you are lucky because now you can go and enjoy and have fun and vacations and forget about that. But in the future, it will haunt you, especially if you want to work there. So it's up to you to correct it, right? It's up to you to correct it. See, the teacher is, I hate to be a policeman. I'm a teacher, an educator, not a policeman. I don't want to Gestapo here to see if you, I'm not like that. So sometimes I give grades and I pass people and so on, but I tell them, it's up to you to correct. You should be your judge, okay? And I tell you by experience because when I was in my undergraduate, some of the teachers I had were horrible, and there was a lot of politics in the university, so the courses were always interrupted and so on. So sometimes I was just fed up. Algebra, just want to get a passing grade. And I would copy, or I would do all sorts of tricks just to get the grade and go on. But then when I started my PhD, I had to cover all that.
Yeah.
Because I could go along. It's like if you live by loans. Yeah, the bank gave me money. I spent it all. Then somebody, credit card, money, I spent. There comes a time you have to pay all these debts.
Yeah.
So if you accumulate all these debts, then it's going to be like that. So if you do some misdemeanor, try to correct it. Okay? Okay. Enough of counseling. Now let's go back here.
Yes.
Okay, we've seen. Yes. Okay. Now let's go to the next. The Hubble diagram also show this,
Yes.
and the fact that we compare coefficients, because essentially what happens is that for supernovae that are very close, all the models give similar predictions. But once we start looking at supernovae that are far away, then it becomes interesting, because we can really start using these supernovae to discriminate models. Okay? Now, we've seen all this. We've seen all these expansions of the scalars, the Weil tensor, the shear tensor. We know that the LTV models are determined by these scalars. The only difference is that we've called this guy we call psi2. It's just a question of notation. And then we can reduce the dynamics of the models to purely scalar equations. We've seen that. We've seen those equations. We've seen, in fact, even numerical solutions to them. Now, we've seen also these equations, the 1+3 equations. These are evolution equations. This is the Hamiltonian constraint, Friedman equation. These are the momentum or space-like constraints. We've seen all this. This is just a review, right? Now, LTV models have these scalars, and these are common scalars with FLRW. FLRW has these scalars: spatial curvature, Hubble, and density, right? This also exists for FLRW models. But shear and electric Weyl tensor are 0 for Freeman, Robertson, Walker. So the difference between these two are contained here, right? Are basically contained here. Okay? So now I have introduced the Q-scalars in a different way. The motivation was the quasi-local mass, right? This integral, you remember? We did the integral for the mass, and then we defined a sort of average. It was a weighted average. But then there is another motivation to derive the Q-scalars. Suppose that we have the 1 plus 3 system that was given above, and we propose a solution of that system that is based on the exact perturbative scheme. See, we say, now we know that this is a solution, but suppose we don't know. See, we have the 1 plus 3 system that was shown before, right? And we propose a solution of this form, right? We propose a solution of this form, and we demand that rho Q and HQ are LTV scalars that satisfy FLRW dynamics. Now we know that they do satisfy FLRW dynamics. But suppose we don't know. We propose a solution of this type for the 1 plus 3 system that was shown before, and we call these two background variables because they are LTV scalars that satisfy FLRW dynamics. And we call them background variables, just a name, right? And then these two, because we have now four, we have now four variables, this one and this one, this one and this one, and these two others are obtained. Once we propose this and we throw this ansatz, we throw it into the 1 plus 3 equation, then we get equations for these two. We've seen this, how it works, right? We've seen it, see? And these are obtained from the 1 plus 3 system, and this we call the exact perturbations, right? So let's see how the system works. LTV, the system works very nicely, and this allows us to describe the models as the evolution of exact 1 plus 3 fluid flow perturbations. See, this is the original system, right? See, this is the original 1 plus 3 system. I'm writing it here again. This is the 1 plus 3 system, right? So we substitute this here, right? Substitute this here. We did this in Maple, right? Okay. Now, what is FLRW dynamics? It means that rho Q has to satisfy this, because this is identical, formally identical, to what FLRW scalars would satisfy, right? And it will satisfy also this one. This is the FLRW Raichaduri equation, except that these are LTV scalars. And will satisfy this one. This is the FLRW Friedman equation, right? This is what we are demanding of the Q scalars here, right, that we're going to substitute here. We solve the momentum constraints. See, the momentum constraints, we solve them, and the momentum constraints will imply already that delta A has this form for all the Q scalars. Now, these things were now, this constraint, the solution of these constraints determine this gradient law. We didn't do it like that. We found this gradient law by deriving the integral definition, but it can also be obtained. I don't know if you understand what I'm trying to do. I'm looking at the Q scalars from a different point of view, right? Not the way we saw them, but with this idea that we have the 1 plus 3 system, and we want a solution of this type, right? And we throw this into the system. Okay, we want a solution of this type with this equation satisfied. So we throw all this into here, and the constraints are automatically satisfied. Okay, but this is a different approach, because in the other way, what we did was to define the Q scalars from the quasi-local mass in a different way. But it's the same. And this is a relation between perturbations and gradients, okay? Now, we transform LTV dynamics into evolution equations for covariant, exact covariant perturbations. So what happens? These are the background variables. These are the exact perturbations. These are the evolution. We obtain this. We obtain this in a Maple workshop, right? And notice that these are the evolution equations for some sort of, in fact, I'm hesitant to, again, to use the term perturbations because perturbations, people assume it's approximation. This is exact, right? That's also why I've used the term fluctuations or relative fluctuations. But it is a mathematical mimicking of the perturbation problem, right? We don't have perturbations because it's exact. But we are defining the evolution of exact quantities in a way that looks like the evolution of perturbations. When you have perturbations, this would be the evolution equations of the background. Therefore, all this would be, there is a Q missing here. All this would be equations among FLRW scalars, and this would be the equations, approximate the equations for the perturbations, right? Now, these are the constraints attached to the system, and now what we can see is that this system is a system of ordinary differential equations that has to be satisfied for, that depends on one parameter, that is, it's what I showed you in the program. What I showed you in the Maple programs is that you have to satisfy the evolution equations for each value of the radial coordinate, right? So it is not a simple system of differential equations, because ordinary differential equations, there is no dependence of radius, right? So your initial conditions are constant, right? Now imagine that your initial conditions depend on radius. That means that you have to make a partition of possible values of radius and solve the differential equation for each value, constant value of that partition. Do you understand this? Yeah? Yeah, I see.
No, I can.
You don't understand that. No, well, you have a differential equation. Suppose you have a differential equation. Right? This is a differential equation. But x is a function of t. So what are your initial conditions? X of t0. And these are t0 is a x0 is a constant.
Yeah.
So it's only one solution. Right? It's only one solution. It's a curve. Here you find the solution. Right? This solution will satisfy this, right? Yeah? It will pass through this point. Okay? That's clear? Acha? Now, what happens if x is a function of t and r? And your equation is
Partial differential.
yeah, of course, it's partial. Right? So your conditions will be x of tr r, right? And then you can, what you do is you assign a values to r. You say r is an element of let's say you take your values of r between 0 and 1, right? And you make a partition of this. Say r would be like, I don't know, 0, 0.1, 0.2, etc., right? So you will have, for example, are, and you call them, let's say, you have a partition. So that means that you have to solve this differential equation for every value of r. See, so you will have x of t0, 0, x of t0, 0.1, x of, and this will be called, I don't know, you call this x0, and then you call this x1, and then you call this x2, right? So you have to solve for each value of r that will determine this function here. This is a function, you can choose it. Let's say sine. Okay? So here it would be for 0, it would be 0. For r equals 0.1, it would be sine of 0.1, etc., etc., etc. So that means that if you have a partition of 10, you have to solve 10 ordinary differential equations, right? And this is what happens here. This is the type, it's just what happens, except that instead of one equation, we have four. Four simultaneous nonlinear equations have to be solved for four initial conditions that depend on radius. And then that's a mathematical numerical problem. Okay? Okay, so but never we've seen this. In fact, I've given you Maple files that do that. Okay? Now evolution, these are the evolution equations that we obtain. Now here, the Q scalars that I'm using are density and Hubble. And these are perturbation of density and perturbation of Hubble. And this is the system we have to solve. I showed you that you can add two supplementary equations to obtain also the metric functions, right? This is in the metric files, in the Maple files you have. Okay, so, and these are the constraints. Now, another possibility is, we've seen this, okay, I think. Another possibility is we have this constraint, we have this definition of this. We can define the Q scalar and omega Q scalar, and then once we define this, we apply the gradient rule, and we obtain this constraint between fluctuations, and we can change to other. This is here. We are describing the evolution of the models in terms of these Q scalars and their fluctuations. And then this is another representation that can be useful. This is the omega H representation. So because of the constraints, we can shuffle the Q scalars and construct different but equivalent systems of differential equations. And this can be useful for cosmological applications. Look, I know this is a lot of material, and the important thing is that you understand what I'm doing. Not the details, forget about the details.
Oh, yeah, that's right.
But that you understand what I'm doing. I have the 1+3 system, and the 1+3 system in itself is difficult to handle because of the constraints. Now, I propose an exact perturbation ansatz, and the constraints are automatically satisfied. Therefore, our differential equations are of this type. Are partial differential equations that can be handled as if they were ordinary differential equations. And this is fantastic news to deal with these models, because we can, it's always better to study ordinary differential equations than partial differential equations. Well, these are strictly partial differential equations, but that can be handled as ordinary. And that's the whole thing. If you say, once you go to bed tonight and say, oh, LTV models can be, the dynamics of these models can be handled as if they were ordinary differential equations. I've seen that working. Then I'm happy. Like, that you know that this is possible. details you can always go back. And the scalars that do the trick are the Q scalars. Okay? Now, numerical integration, this is the system we want to integrate. So these are the initial conditions. See, we need to specify this at an initial time, but notice how this initial condition depends on R, just like this one, right? Okay, so just as here we assume that initial condition is a sine function, or a cosine, or a tangent, or a polynomial, or whatever you want, here we have to give a functional form that will depend on R, and this will be initial conditions for this system. And so we need a partition of R, and we need to integrate these differential equations for this value of the partition, right? And
Sir,
yes.
to take initial condition, we should not follow any rule? Any initial
No, yeah, they follow any rule. Like, for example, if you have an initial density, what would you expect? Well, you expect the density to be like this, right? Or to be like this.
Yeah, it will change according to model, no?
It depends on the model and the problem at hand. If you
Yeah,
want to
yeah.
model an overdensity, your initial condition would be like this, right? Okay? You want to model a void, an underdensity, you put initial condition like this. But you're not going to put something arbitrary. No, initial conditions have to be well thought. In any problem, any differential equation, harmonic oscillator, diffusion, heat conduction, quantum mechanics, Schrödinger equation, you have to be careful how you choose your initial conditions. Now, sometimes you don't know, it's a trial and error process, right? But of course, now, you make a choice of radial coordinate, which we made before, but here you can make it at this point. In this choice of coordinate we've made, right? And then you use the gradient law to obtain the initial value of these fluctuations. And these are the initial value of the fluctuations of the perturbations. You find them using the gradient law because this is satisfied by these Q scalars. And then we have 4 ordinary differential equations with a 1 parameter set of conditions. This is what I'm describing here. Initial conditions that depend on 1 parameter, right? Now, as I'll hope to have time to show, in Secularist levels, the space of initial conditions is 3-dimensional, right? So it's much more complicated. But in spherical symmetry is 1 parameter. So 1 parameter family of initial conditions. Initial conditions depend on 1 parameter. Okay? So what will we do with this? Well, also remember that we have analytic work. We can do a lot of analytic work, especially if lambda is 0. This is the metric that we're considering. This is the scale factor, and this is the other scale factor here. And we have these initial conditions also. And we know that all these Q scalars can satisfy all these laws. We can also compute them analytically, as long as we know the scale factors, right? But there are analytic solutions for the scale factors. So this can also, there's a lot of analytic work that can be done. And even in the omega representation, that is, once we have a form for gamma and A, we can compute all these things analytically, right? Okay? But the main idea is, okay, interpretation, there's something very interesting here. We mentioned that the Q scalars are related to averages. So let's see, this is the definition for the Q scalars, right? And we already seen that. This is the proper volume. So it's like an average with a weight factor. The weight factor has this form, therefore it is an invariant quantity. And the interpretation is as follows. This is a time. This is a force velocity, which is our time axis. This is our space axis, which is the space that is orthogonal to the force velocity. And here we have a 2-sphere. This is a 2-sphere, right? and this is a following two-sphere, a near neighboring two-sphere, and this is the normal vector to the two-sphere that is also normal to the four velocity, and is also orthogonal to the four velocity, and is orthogonal to the two-sphere, right? This is, now, what we have is a comparison between the local value of A here and the weighted average of A, and see, we compute this, and this will be the average with weight factor of this domain, and we are comparing the local value of A with its weighted average at each two-sphere. This is how we form these fluctuations, right? And what we do have is, we can do this for every two-sphere, because what we have is a foliation of this three-dimensional surface is foliated, which means it's like filled. It's like filled with these two spheres. And at each two-sphere, we make the comparison between the value of A at the two-sphere and its average. This is very standard procedure in, for example, in statistical mechanics. You have a local value of the temperature and an average temperature. That gives you what in statistical mechanics is called the fluctuation of the temperature, right? So we do exactly the same, except that it's not thermodynamics. What we're comparing is basically the density, the Hubble factor, the Hubble scalar, the spatial curvature, and the omega Q scalars that we are constructing. All these quantities, we compare the local values with the averages. And this gives rise to fluctuations, see? And so what's the trick about the averages? Well, the averages, the interesting property of the averages is that they satisfy FLRW dynamics, see? So this is rather very useful description. Now, perturbation formalism, this I'll see very quickly. How do you define perturbations? Well, strict, rigorous, if you talk to people who Newtonian and so on, perturbation is background value times multiplied times 1 plus a small correction. And they say, you substitute this in the dynamics, and then you get the equations for the perturbations. But this works in flat space. In curved space, where you have the liberty of, you might, for example, if you just do this, see, what I'm saying is that the naive approach to perturbations would be, and you have some dynamical equations. You have some dynamical equations, very complicated. You have a dynamical equation A dot equals blah blah blah, B dot equals blah blah blah, C equals blah blah blah, and it's horrible. Horrible. All this is horrible, right? Horrible equations. 3 blocks, they extend, they cover 40 blackboards. They're horrible. They're longer than your papers. So what do people do? Say, it is so horrible that I'm going to propose a solution of this form. And let's say that A depends on T and R. So I'm going to propose A0 of T plus delta A. And the same for B. B0 of T plus delta B, etc. And we're going to say that delta A is much smaller than 1, delta B is much smaller than 1, etc. Why they do this? So that if you do this, then a term like this will be much larger than this, right? Will be much larger than this. No, sorry, something. So you plug this into the equations, right? So this decomposes in equations for the background, right? But these are ODEs, right? Why they are ODEs? Because this depends only on time, right? And C0, okay, it's an ODE. But then you have an equation for you have an equation, horrible. And then you have an equation of this type, again horrible, and an equation of this type, right? So these are ODEs, so they are simple to solve. Okay, even if they are non-linear, they can be solved. Okay, now these are horrible things, but because of this assumption, this can be simplified because every term of the form or all these terms can be neglected. See? Because what happens if something is very small? 1/10, and you multiply times something that is also very small. The product is even smaller, or the square is even smaller, or the cube is even smaller. So you remove all these things, and therefore this reduces to partial differential equations that are linear. And all partial differential equations that are linear are manageable, are quite manageable. They are very, very good techniques to solve it, right? So this is a typical approach to perturbations. Now, if you compare what we have done, is something similar, except that we are not making this assumption, right? We are not making this assumption. We still have, this is an approximation because delta A and delta B need not be small. But we assume they are small. In certain conditions, you can do that. Like what would be the case in cosmology? You assume that density is a sort of average value that would be A0 plus some corrections. And you assume that these corrections are small, that there is not, deviation from the average is very small. So you can reduce dynamical equations to background equations. These are the background equations and the equations for the perturbations. What we have for LTV models is mathematically the same, except that the equations for the perturbations are exact. And they are essentially, they are partial differential equations that can be handled as ordinary differential equations. Okay? This is not true in general, but for LTV models using Q-scalars, it happens. Now, what's the problem when you do this in curved spacetime? The problem is that in curved spacetime, if your quantities are not covariant, then everything can disappear if you change coordinates. So people can ask you, how come your equations, can you guarantee that your equations are correct even if you change coordinates? Or maybe what you are describing in these equations is some possible change or some spurious, some non-dynamical degree of freedom that depends on your ability to change coordinates. So there is the standard way to define perturbations. It's not like this. This is like an ansatz. And it can work in many cases, but in general relativity, it's not sufficient. So there is one mechanism to define them, and it's through a map. We're mapping two spacetimes. We're mapping two spacetimes, but we're mapping, it is not a mapping of the spacetimes. It's a point-to-point mapping, but mapping of functions. It's what is called a functional map. The space of all functions is mapped to the space of all functions. See, I'm mapping the space of all functions that can be covariant scalars that can be defined in an FLRW model to the set of all covariant scalars that can be defined in LTV models. And the map will associate the scalar, the Freeman-Robertson-Walker scalar, with the Q scalar that it's corresponding to Q scalar. For example, the FLRW density will be mapped to the quasi-local density of of the LTV model. And this is how we can formally, rigorously define the Q-scalars we can define them formally as exact perturbations. Anyway, this is, yeah, I'm not going to stop here, but this is just to show you that the Q-scalars can be rigorously defined in terms of functional analysis as exact perturbations. There is a formalism. All perturbations that people use in relativity satisfy this criteria. But a lot of people don't know that. They simply use perturbations. But I don't want to go into this because there are other interesting things. Now, there's one important thing that once we look at the dynamics of the models in terms of Q-scalars, and we realize that Q-scalars mathematically behave like they behave mathematically like exact perturbations. So, has any one of you worked with perturbations?
Some classical perturbations. Some classical perturbations.
Of what?
Of the orbit of.
The orbit of a planet?
Yeah.
Okay.
And in quantum
The
mechanics.
precision of ellipse.
Cosmological perturbation of the second order.
Yeah, okay, that's good, because then you'll understand what I'm going to say. The point is this. We have this, the Q-scalars that we have are like this. Okay? Q-scalars we have are rho Q dot equals minus 3 rho Q HQ. And we also have HQ dot plus minus HQ squared plus, no, sorry, minus 4 pi by 3 rho Q plus 8 pi 3 flat. And then we have equations for d rho. I don't remember it, I think it's something like this. And we have something dh, which I don't remember the exact. So this is what we have, right? So now, if we assume that rho is almost, let's say that we assume that rho is almost equal to the, we know that the limit when r goes to infinity of rho q is the background value, and the same for h, right? The limit of this thing, we get the background value, see? Right? See, what we're assuming that this is the time axis, this is the radial axis, and here are the dust layers, right? Okay, here density is very high. But as we move in this direction, the density, not only both densities approach a background value, see? That is, if we plot the density in any of these surfaces, what we will see is something like this. Right? Let's say the rho Q and the rho density. We see that if we get very far away, then we approach a background value, right? Okay. The physics is that we have an overdensity. It can be very dense, but if we get far away from it, far away, we reach the FLRW background, right? So we have this, and we also have this limit. and this depends on time. Right? These are the background values. See? We go very far. This is t equals const. At every surface of constant time, we get this convergence, right? This is something that you even impose on physical ground. Because you have an overdensity that is evolving, but you want that if you go far away, far away, far away from the overdensity, background, right? Overdensity over there. Here and in the background, right? Okay? So you assume that, you impose that condition. But then what happens is that both densities, which are different, one is an average, the other is a local value, they are different, right? But what happens as you go where R is large? What happens when R is large? The two densities differ very little, right? What you have then is that rho is approximately equal to rho Q, approximately equal to background value, right? Okay? So what happens with these two equations? These two equations become almost the effort. But before that, what happens in these conditions? Well, in these conditions, how is delta rho? This will be much smaller than 1, right? Because the two densities approach each other as we go towards the background, right? The two densities approach each other.
That means rho minus rho Q goes to 0.
It goes to 0 in the background, at infinity.
Yeah, in
but
background.
if we don't reach quite yet infinity, but very large, they become very small, right? Become very small. And then, and the same thing for H, becomes very small, right? The same thing. So, these two equations will reduce to purely ordinary differential equations, right? What would happen in this condition is that, can I erase this? People saw this? Okay. What happens in these conditions is that these two equations would become something like approximately right? These two equations would approximate these two, right? Okay? And these two would become linear, right? Because see what happens here? Here we have a product, delta rho, delta H. But what happens if these are two very small? So this linearize, right? Now what we can show, and this is a good exercise for you to do, if this become linear, and we combine these equations, the four of them together, we combine them algebraically, we get this very nice equation. I'm not sure, there might be a sign error. Let's make lambda equals 0 now. Let's take lambda equals 0 to avoid problems, okay? To make it simpler. get this very simple equation. This is the equation, this is the density perturbation. This is the equation that is satisfied by dust, density perturbations of dust sources. And it can also be obtained in Newtonian physics. Now, the solution for this equation is something of this form. The solution is, and let me check that I'm using the, I just want to check that I'm using the, okay. The solution for this equation has, because this is linear, it has a solution of this form. It has a solution of this form. Because it's linear, then its solution is a superposition. This, the difference is that this j of t, it's a growing function. And this, this negative one is a decay. This, in fact, yeah, this is a function of r only. This is a function of r. But here we have functions of time. And this function is a growing function. And this function is a decaying function. So what we know is that the density perturbation is a combination of a growing function, growing in time, and one that is decaying on time, right? So this thing here, the j, this j is called the growing mode, and the other is the decaying mode, right? Okay? It is very, very common to assume that, so if we add them together, if we plot them, see this is d rho, if we plot them, what we will see is that, say, this is the decaying mode. This is j minus of t. And the growing mode would be doing something like this. This is the j plus of t, okay? And here is, let's say, is the Big Bang time, right? So this is bad. Why? Because it means that the perturbation becomes infinite at the Big Bang. And perturbations have to be small, right? You agree? Perturbations have to be small. So this is unphysical. Not good. So people normally take initial conditions so that C0 is 0. We only have a growing mode. Okay? It is, strictly speaking, not necessary, because you could argue that you are not interested in this bit of the evolution, but only in this bit. If you say that, then you can keep a decaying mode, right? But otherwise, if you are interested in looking at the evolution all the way to the Big Bang, then you have to remove the decaying mode, right? And then you only take the growing mode, right? Take the only. Now, perturbation, the linear regime, is not valid through, it's just an approximation. Notice that these are approximated solutions. Always perturbation is approximated solutions. Perturbations are not exact solutions, right? Okay? But so this is very important. The density perturbation that we obtain by linearizing these equations has this form. The density perturbation has this form. See? It has the form Jg growing mode plus Jd decaying mode. It has this form. It is an approximation, right? And it comes from linearizing. And you find this, you should know that. You work with cosmological perturbations, you've seen that equation, right? Can confirm. Yeah? He can confirm I'm not talking nonsense. Okay? Now, what happens with LTV models? With LTV models, we're claiming that we are describing exact perturbations. So how do the exact perturbations relate to the non-exact perturbations, to the approximated, to perturbations that, well, you can write the density perturbation that we have defined, you can write it in this form, where the growing mode, you can identify, you can write it in this form, and here, see, if it was linear, what would happen? Okay, let me write the whole thing. So
J's are quadratic equations.
what?
Are J's quadratic equations or Bessel function?
No, neither.
Okay.
They're not Bessel. What did you take? Bessel? There are no Bessel functions here. Bessel functions appear in cylindrical problems.
Is it quadratic?
No, it's not. Look at them. Don't guess. Quadratic, Bessel,
This
hypergeometric.
is the graph.
No, these are not Bessel. Yeah, I see. Because Bessel functions are written with J. No, they're not. No, just notation. Just notation. No Bessel functions. Sorry. No. I understand your error now. No Bessel functions. It's just notation. Okay, right? Like I can call myself. I don't know. I can call myself Nehru. That means I'm Nehru. Just notation. Okay. Okay. So we can identify. We can write this fellow here, because in the case lambda equal to 0, we have an analytic expression for this. So we can write this quantity in this form. Right? Notice what happens when JG and JD become very small. They become very small, so our perturbation will be the sum of them. Right? That would happen in the linear limit. But in the exact case, the expression we have is this one, which is non-linear. This is non-linear, right? And then we can identify the growing mode. It is this quantity. It's h cubed multiplied times t, etc. It's this quantity, and this is the equivalent to the c plus, c minus. It is the G0. And the decaying mode will be this function. It is decaying because H is a whole expansion. It's infinite at the Big Bang, and then it becomes 0. It decays, right? So this has a behavior of a decaying mode. Here. This one here, and this one is